Introduction's already out of the way. We'll just jump into the topic for today. The slide titles may be a little bit different. I'm recycling some material here, but let me start with the first word that you see, TrustDER. This is a project that's being funded by US Department of Energy, Office of Electricity, and the intent is to create a coordination stack for DER devices. So, batteries, solar panels, etc. How do you coordinate them in a manner that you preserve the privacy of the owner and the security of the device? So it's a multi-layer computational computing architecture stack addressing security at every single one of those layers. And the particular task that I'm working on within that project is task 3 called Secure ID, which entails development of an identity management system for those devices. And I'll talk about that in this talk today. So real quick, agenda, give you a little bit of background on what we are trying to do, what the current state of things is, what are some pros and cons of the current approaches being used in this space, what our solution looks like, and the work we have completed thus far, what we are doing next. So background in current issues, this slide is probably too high level for the audience here, but we'll go through it anyway. What is an identity management system? So it's foundational infrastructure for interactions between entities, and entities could be a broad set of things, could be organizations, users, devices, and or services. In the context of what we are discussing today, it is devices for us, and particularly for TrustDER, those devices happen to be batteries, but there's no reason why this could not be applicable to EVs, charging stations, photovoltaic panels, thermostats, smart thermostats. It could be any number of devices. It could also be grid assets like transformers, etc. In terms of what an IDMS must support, it should allow the entities to authenticate themselves. It should be able to share the authentication results with other entities, and it should maintain and protect a registry of credentials. And the last one, that registry of credentials, is very particular to centralized systems, but let's for now go with that feature. Of course, with traditional identity management systems in centralized systems, you store credentials for each of those entities, and you create a privileged system with disproportionate control and a well-defined target of cyber attacks. What we are trying to do with Secure ID, we are developing a distributed identity management system, which will do the identity provisioning. It will authenticate, it'll authorize devices, and allow identity data to be shared across devices on that network. The focus of the presentation today is going to be exclusively on the authentication protocol that we have developed, and I'll share more details of what that looks like. Before I jump into the rest of the presentation, maybe it's important to mention that this identity protocol runs on a blockchain network. We'll talk very little about blockchain part of that today, and we'll talk extensively about the actual protocol that allows that identity verification to happen. A high-level overview of security in computing systems. Defense in depth security model has been widely adopted in IT organizations around the world. And lately, we are seeing adoption for industrial control systems as well. And fundamentally, what this boils down to is you implement security at every single layer of the computational architecture, as well as policies and procedures. So you start with the application and data security. You have the host security, so the computer that's hosting your applications and data, the network security for the network that's hosting that computer, physical access to that data center where that network is placed, and then governance layer around it. And combined with all these layers, we assure some guarantees or risk-based sort of assurances around what the security of the entire system is. Identity is just one part of this system. And within the context of identity, what we do today for centralized systems is we have 3 sort of key mechanisms that I would say are super robust in terms of preserving and maintaining identity of devices. One is using a hardware-based solution, which is a secure non-volatile memory, combined with some hardware for cryptographic operations. Recently, we've seen a surge of use of physically unclonable functions. So we'll go into that as well. And a special case of physically unclonable functions is physically obfuscated keys. So let's talk about each of these, what they look like, what the pros and cons of these are, and then discuss how do we take the advantages of these approaches and then implement in a distributed identity management system to perform authentication. Current best practice is NVM plus hardware cryptography. So effectively, you take a secret, and I'm going to use the term secret, secret key, identity information, all interchangeably, because in the end, it comes down to key management. Your password or whatever that secret is. Where do I store it? How do I store it securely? How do I maintain privacy of the device that is identified by that secret? And how do I allow that device to be authenticated? So you basically take the secret and you put the secret in a non-volatile, electrically erasable, programmable read-only memory. Or you can put it in a battery-backed SRAM, static random access memory. On top of that, you use some sort of hardware that performs cryptographic operations or digital signature encryption, etc., on top of where the key is stored. And that's typically how you would sort of secure this key or secure the secret. The limitations, of course, are it's expensive both in terms of design area and power consumption. It's an entirely hardware-based solution. It's expensive to manufacture because NVMe EPROMs require additional mask layers, and battery-backed SRAMs require an always-on external power source that adds to the device, especially when we are talking about small IoT devices in the range of like $20 to $50 MSRP. This becomes incredibly expensive and is a significant source of cost if we are to protect those devices. Then we have, on these devices, we are doing digital signatures that require expensive cryptographic hardware to implement, because this is we are using a hardware-based cryptographic solution. And yet these devices with all those costs are vulnerable to invasive attack mechanisms. So if a physical control is not in place, then the device can be tampered with and the identity can be compromised. To protect against such physical attacks, you want to put in some active tamper detection or prevention circuitry, which again adds to the cost and needs to be continuously powered. So it's a super expensive hardware solution. It's worthwhile implementing for high, device costs where $100 or above, but when it comes to cheaper devices, it is not a viable solution. And let me also say, I'm talking about these approaches only to set up what we are doing in the sense that we want to go from hardware to a completely information theoretic approach while maintaining all the advantages that hardware provides. So that's why I'm going through the setup. The second thing I want to talk about is physically unclonable functions, or PUFs. So PUFs are based on this idea that even though the mask and manufacturing process is the same among different ICs, each IC is slightly different due to the normal manufacturing variability. And therefore, PUFs can be leveraged. We can leverage this variability in PUFs to derive secret information about the device that is unique to the chip itself, or think of it as a silicon biometric. And advantages of using PUFs are the hardware is, PUF hardware uses very simple digital circuits. A lot of PUFs typically use NAND gates, for instance, that are super cheap to fabricate and derive identity information from. PUF hardware consumes less power than comparable EEPROM or SRAM-based solutions. PUF applications do not require the use of digital signatures. If the device is off, it doesn't need to be protected because it can never serve its identity to anybody. Since the identity is derived from the physical characteristics of ICs, the device must be powered on because the secret resides, for the secret to even come up in memory. So for a powered off device, even a physical intrusive attack will not reveal the PUF. And that's what makes PUFs super interesting as a mechanism to produce identity information or provision identities. Limitations of PUFs, they are prone to degradation based on environmental conditions. So there are several kinds of PUFs, and each of those would be susceptible to certain environmental conditions. A delay PUF, for instance, will be susceptible to capacitor degradation on a network or on a circuit. So depending on what type of PUF you are using, they may degrade over time. It is challenging to implement PUFs in untrusted networks. And PUF-based authentication speeds are inversely proportional to the number of CRPs. So CRPs are challenge response pairs. And the way a PUF function is modeled, you basically issue a challenge to the function and the function responds back with a response. And somewhere else outside of the device, one needs to maintain a map of all the challenges against all the responses. And the bigger that map gets, the slower the puff authentication speeds are. So to solve that last problem, we also see implementation of physically obfuscated keys, which is a basically special case of a puff. So if puff can be modeled as a black box challenge response system where R equals FC, so R is the response that you receive from the function F, and C is the challenge that you supply to that function, then POKs are special case of puffs that can only process one single challenge. So your CRP map effectively is a one row, which makes it really fast to perform authentication because there's only one check you have to perform. You don't have to go through a list of challenge response pairs. Just like puffs, POCs are direct digitization of some aspect of underlying hardware. Could be NAND gates, could be butterfly puffs, could be SRAM puffs. There's n number of puffs, and new ones seem to keep coming up. It's easier to implement due to the small number of CRPs. The response times are faster. We talked about that. But POCs share all the limitations of puffs other than the one around speed. So very similar, but a special case of the previous technique anyway. What we want to be able to do is we want a software-only information theoretic approach that allows device identity to be verified by the network participants without the need to imprint credentials in silicon. So we want to take hardware out of the equation and be able to provide similar guarantees, similar security as a hardware-based solution would do. And this, we are calling this solution Keymaker protocol, which is effectively a social verification smart contract and protocol for decentralized network devices. It's a mouthful, but effectively what that means is we run these devices that we are trying to authenticate on a blockchain network. On this network is a smart contract. That smart contract allows devices to be verified by other devices on the network. So at a very high level, Keymaker is a set of smart contracts, protocols, and library functions that create multiple shards of a device identity or device key or device secret. So you take a secret, you split that into multiple smaller shards. You then distribute these shards to adjacent nodes on the network. And then you enable the adjacent network nodes to combine these shards and verify the identity of the device. And I'll walk through step by step what that entails. But simply speaking, we are using a social verification mechanism where these devices all belong to this blockchain network. And other devices on the network, so let's say I'm a device on the network, other devices on the network can then combine their shards of my identity to verify that the identity that I'm presenting to the network is accurate or correct. The underlying technique that we have used is Shamir secret sharing, developed by Adi Shamir in 1979. Adi Shamir is the S of RSA, by the way. This super old technique, but we've packaged it in an incredibly innovative way, we think, with symmetric encryption to be able to do identity verification in a manner that provides us perfect secrecy in a blockchain network. A little bit of definitions before we jump into the rest of this presentation. So I kind of mentioned this. I'm going to use secret key, private key, device key, all interchangeably. And this is effectively the identifier that needs to be sharded by the smart contract. We have a secret owner, which is the device that initiates the Keymaker protocol to create those shards. Then we have the shards themselves, which are single encrypted share of the key. So usually the shards themselves are encrypted, even though in the examples that I'll use today, I won't really talk about the encryption there. Shard custodian or a shard holder is a peer device that holds the shard, and it's generally a device on a trusted network, within that broader blockchain network. And a custodian is a device that holds the complete key or multiple keys for itself or for its peers. So let's consider an example of how we would use simple sharding to perform this social verification. Let's say that our device key is 1, 2, 3, 4, 5, 6. And let's say there are 3 nodes on our network. And I simply would take the key and I would shard it into 3 smaller shards, 1, 2, 3, 4, and 5, 6. Now, the biggest challenge in this implementation for simple sharding is that each of the shards are required to perform the verification. So if device 1, device 2, device 3 all have to be online and all have to respond to a verification call and present these shards for me to verify the identity of this key. if any of these devices is down for maintenance or unavailable or compromised, I cannot even verify the identity of a device that may not be compromised. So to solve this problem, of course, we can implement simple sharding in a different way. We can say the device key is still 1, 2, 3, 4, 5, 6. The network, the number of shards I have to produce are still 3. But let's also introduce this new variable k equals 2, wherein we say only 2 of those 3 shards are required to perform social verification. In this case, our shards look a little bit different. This is a typo, so ignore this, but the shards look a little bit different. The shards look like this: 1, 2, 3, 4, and 2 spaces, 2 spaces, 3, 4, 5, 6, and 1, 2, 2 spaces, 5, 6. And now I can take any 2 of these shards and be able to combine them to reproduce the key and perform social verification. And so that solves the problem that we had previously, where all devices had to be online, and we have introduced this new variable k, where k less than n devices needs to be online for me to perform social verification. But in doing so, I have now violated perfect secrecy, meaning, so if I go back here, and let's say one or let's say 2 of these devices, let's say one device decides to be a bad actor and wants to be able to reproduce the key. In this example, it would have to make 10,000 guesses to be able to reproduce this key. But as we increase the size of the shard, now that same device only has to make 100 guesses, thereby violating perfect secrecy clause of information theory. And the clause basically says that a crypto system is considered crypto-analytically unbreakable if a shard does not have enough information to produce the key, even with unlimited computing power. In the simple sharding technique that we discussed, as we increase the size of the shard, the likelihood of the amount of computing power required to guess the key is lower and lower. The other issue with simple sharding is the devices could decide to corroborate against against the device that we are trying to protect. And so in this case, you just need 2 devices to corroborate together to reproduce the key. And we don't want that to happen either. So what is our solution to this? Well, before the solution, let's set some constraints on what our system needs to be able to do. And then let's go into the details of how we do it. So the main idea behind Keymaker protocol is to break into shards, and those shards must have the following properties. We must only require k shards to perform social verification of a secret. K is less than n, where n is the total number of shards being distributed to custodians. Any shard SX, S1, S2, S3, all the way to Sn must not be a subset of the key. And all shards S1, S2, all the way to Sn, when combined together, must not reveal the secret key. So I typically pause here because these are very conflicting set of requirements. What we are saying effectively here is, I should be able to take a subset of the shards and be able to verify the device, but all the shards combined together should not be able to reproduce the key. And that's almost intuitively seems like an impossible set of requirements. It is impossible when you use simple sharding techniques. It is possible when we start using computational sharding techniques. So what we are doing here, I'm gonna skip this slide or just quickly talk about this here. So this was the simple sharding technique, and it fails every single one of our constraints. Only k shards are required to perform social verification of the key. K less than n, of course, that's not true. We need all the shards n to perform social verification. Any shard SX must not be a subset of the key. Each of these shards are subsets of the keys. And all shards, when combined together, must not reveal the key. In this case, all shards combined together do reveal the key. So in simple sharding, it is impossible to meet these constraints, any kind of simple sharding. So what we do is we implement some secret sharing, which is a mechanism to produce computational shards. And here's how we do it. So we take the key and we first place it on the y-intercept. Then we generate a random point in that plane. We draw a line on that point, and then we take 3 other points on that line. We can take, there's infinite points on that line. We just take 3, and we distribute each of those points as a shard. And now when we are to perform social verification, any of the 2 shards could reproduce that same line for us, but only the device in question that needs to be verified knows that the identity is on the y-intercept. So the device can take its own shard with any shard on the network as a base case. We take the comparative as two other shards on the network. And if they both produce the same line or the same curve, then we know that the identity that this device is presenting to the network is the identity that it claims to have. And so this is the super simple implementation of Shamir secret sharing. Of course, we can increase K, and n can be infinite anyway because we are drawing curves on an infinite plane, but we can increase K. So when we move to a Kn secret sharing, so 3n case. So this was a 2n case. Only two shards are required to verify the identity. Let's say what happens when we require 3 shards to verify the identity. We do the same thing. We put the key on the y-intercept, but instead of generating 1 random point now, we generate 2 random points, and now we have the curve. This unique curve now has infinite points on it. We take any number of points. In this case, we are taking 5 points. We distribute them as shards. And now we have a 3-5 scheme where only 3 of these points are required to reproduce the curve and thereby allow me to check that the key being presented is on the y-intercept of that curve. So we didn't stop there. There's a issue with implementing this as a smart contract. And the issue is in an event where there is a key loss scenario, so the device that's holding this key lost the key, there is no mechanism to recover the key if we are to simply use Shamir secret sharing for implementation for social verification. So what we do instead is we take this model wherein we combine Shamir secret sharing with authenticated encryption or symmetric encryption. And effectively what we do is this: we still have the identity or the secret that we are trying to authenticate against. We generate another random key. The device that owns the identity generates another random key. And instead of passing this key through Shamir secret sharing, we pass the random key through Shamir secret sharing to, I'm sorry, I don't know why the slides are. Okay, so we take the random key, we pass it through Shamir secret sharing, and we produce the shards. We then take the actual identity of the device and pass it through symmetric encryption to produce a cipher. We append the cipher to each of the shards, and we distribute this concatenated shard to the device on the to neighboring devices on the network. And what this allows us to do is it never reveals any shard belonging to the identity of the device. It allows this key to be used to recover the identity of the device in a key loss scenario. And it still allows for us to perform social verification of this key by just utilizing the shards that are distributed on the network, because we can still produce the same slope that we discussed earlier, or same curve that we discussed earlier. So here's the steps for the actual implementation. We generate a random key. We split the random key into n+1 shards using Shamir secret sharing. Why n+1 shards? Because we want to distribute n shards to the network, and we want to keep 1 shard for the device itself. This is the shard that the device presents to n-1 shards in the network to build that curve up, and that's how we confirm that the device identity is correct. We encrypt the identity of the device using random key as encrypted key for symmetric, as an encryption key for symmetric encryption algorithm. We used SALT's secret box functions and xSalsa20 stream ciphers for this. And for the authentication code, we used poly 1305 message authentication code. We append the shard with the resulting cipher, and we distribute the n shards to the network nodes and store 1 shard on the originating device. Applications of this are wide. I mean, we wrote stuff here categorically, but we can go into each of these examples and find further concrete use cases, more granular use cases. But anywhere, since we're focused on the grid, anywhere we need identity verification while preserving the privacy of the device, meaning only 1 copy of that identity needs to exist on the network. And that's key. So in centralized systems, you have a password or whatever else, you need 2 copies. You need to have a copy and somebody else needs to have a copy. We basically now have performed verification of identity using only 1 copy of the identity itself, only the node that holds it. Nobody else has that identity. And that's key. So any use cases where you only need to keep that one copy to completely preserve the privacy of the owner and still be able to perform identity verification is a good use case. Of course, things written here are grid focus, so grid asset communication security to prevent against false data injection attacks. Any data coming from a device can be signed with this identity, and we can confirm that the data that this device is sending is the one that we receive. Autonomous demand response scenarios, so control signals being sent to thermostats to change their settings, for instance. Proof of generation, so as we have solar panels, deeper penetration of photovoltaics on the distribution network, the grid needs to be aware of how much generation is happening to be able to balance load. And that proof of generation could be signed with device identity that's producing that generation. Vehicle-to-vehicle data sharing among in a deep AV scenario, I think that's more relevant to this group. But even beyond energy or the grid, this is this is not specific to energy. The solution can be implemented for any IoT device, really, where you want to perform identity verification while only keeping one copy of that identity. So the work we have completed thus far, it's a research project. So we did extensive literature review on puffs and how they could be used for device signature or identity. So the identity that we have been talking about all along is actually a puff-derived identity to begin with. We've reviewed a ton of verification techniques, looked at the mathematics behind how cost-effective they are, computationally speaking, to run on devices, and can they run on low-cost devices. And we took all of that input and we developed the code for what you saw earlier, the algorithm that you saw earlier, in a Jupyter notebook environment, and that's where we are at right now. The next step is for us to deploy a testnet. So we are taking this code and now putting it on Raspberry Pi devices in our distributed energy resources lab that we have at SLAC. And we're going to run this on an actual blockchain network as opposed to in a Jupyter notebook, just simulating the network. And we are also getting ready to get the GitHub repository set up with the license assignment. So this work can be shared with anybody else. And that's really it. That's all of my presentation. Kelly, how do we want to manage questions?
Yeah, if everyone just wants to submit questions in the chat and just make sure you're sending them to everyone, we can answer them that way.
Sounds good.
Okay, so first question, do you know what license you're planning on?
It's going to be a BSD2 variant license. All of the work that's being done at SLAC is open science work and funded through Department of Energy. So we have an obligation to release it unless it's related to national security. So this would be open source, and BSD2 compliant licenses, I think, what gets put on it.
Okay, great. Next question is, how far are you from full prove out?
So we have proven it mathematically, and we do have it running in a simulated sort of blockchain network on a Jupyter notebook. I expect maybe in 6 months. We would release the code in GitHub sooner, but we would have testnet and mainnet in about 6 months. Okay.
Next question is, why don't you sign each shard instead of appending the cipher?
We could sign each shard, but we can do recoverability in a key loss scenario. So we want to be able to recover the key if the only copy of that key is lost for whatever reason. And to be able to do that, we don't want to actually shard the key itself because we won't know where the key is stored. Because since this is running on a distributed network, we have to keep in mind that this code is running on every single device. And if in the code we mention that the key is on the y-intercept, then every device would know that the key is on the y-intercept, and we can't share that information.
Okay, thank you. I think that's all the questions we have so far. Does anyone have any other questions?
This is Chris. I have one if you can hear me.
Yes, we can hear you.
Yeah, good, great presentation. Thank you. There's obviously an awful lot of overlap between the kinds of things we're thinking about with driving and mobility, which is essentially an edge network, and the work that SLAC is doing that really started with energy and distributed energy resources. But there are some differences with mobility and energy resources. While a power plant or a solar installation or a windmill isn't moving around, a vehicle is. Can you discuss and share your thoughts on how this might apply to mobile devices moving around, forming sort of local ad hoc networks that need very, very fast speeds for things like autonomous driving, for sharing an obstacle in front or a position that could be used by an adjacent car?
Yeah, so I think one of the key things when it comes to mobility, particularly for autonomous vehicles, is be able to share the results of a partial neural network that each of the cars is running, for instance. And the big threat to that, to that not functioning well, is a false data injection attack. So if a car is trying to share information about its environment with another car in the vicinity, you want to make sure that the data that that car is sending you can be trusted and is the data that that car actually sent to you. And to that extent, the identity in this protocol could be used to sign that data packet that is being sent and be able to quickly verify that the device that's sending the data to you is the device that it claims to be, and the data that you've received is the data that was sent to you. So you can do both of those verifications in one single execution of the smart contract. And I think in that sense, it prevents it prevents against false data injection attacks. The other thing I can think of is the location information itself is super useful. And you can do something similar with that, where location information, as it's being transmitted and shared with other devices on this network, is being signed by the identity, the same secret that's being verified here. Chris, does that answer your question, or were you thinking of something else?
Sorry, yeah, that exactly does. That's really interesting. We've always said that this combination of identity and location was sort of really unlocked all the use cases for the mobile ecosystem. So yeah, that's perfect. Thanks.
Cool.
Great. We have another question. Do you have a perspective on opening this beyond a trusted network, i.e. VPP energy models, potentially interoperating with verifiable credentials for consent-based control?
Not at the moment. That could be the direction we could take towards the end of the project. Right now, we want to implement it and get a demo working within a trusted network. And we do have funds allocated to perform red teaming on that. Based on the results of red teaming activities on what we have done so far, we'll make a decision on which direction to take.
All right. Any other questions anyone wants to ask?
The other obvious maybe mobility sort of energy use case is sharing credentials for charging, so the vehicles and the charging stations. Any thoughts on that particular use case or application?
Absolutely. So we actually are crafting a concept paper around that, wherein we want to talk about this anytime, anywhere demand response. Because we have batteries moving on wheels, we could envision creating a network of cars, basically EVs, and charging stations, and creating a off-chain application that only dispatches the cars towards certain stations for charging, or dispatches to different substations on the grid for discharging when that's available, to do anytime, anywhere demand response. So basically, Uber for energy, if you will, charge your car in Menlo Park where it's sunny, and drive it up to San Francisco and discharge it there, and take a cut out of your services to move energy around.
All right, we have a few more questions. Are you planning to take it from the cloud, networking, etc.?
I'm not sure I understand. What's the question?
That's all they asked. Just, are you
planning? Hi, Mayank. This is Chandan.
Hi.
So we have a cloud setup where the data movement are controlled, and it keeps safe from all the hacking. So that's what I was trying to understand.
Yeah, so we are running it on a decentralized network, and the intent behind doing that is informed by this idea that the devices that we are working with, photovoltaics, EVs, charging stations, batteries at home, power walls, etc., are owned by different entities. So to bring all those devices into a centralized identity management system has been a challenge, and I do not think we'll succeed at doing that in the future. So what we need to do is allow each of these participants or device owners to register their devices on this blockchain-based decentralized network. And when they do that, still be able to preserve the privacy of the owner that owns the device and the privacy of the device itself. So in that sense, we are not looking at any centralized networks or operating anything in the cloud that allows centralized control of any of these devices.
All right.
Thank you, Mayank.
You're welcome.
Another question, is there a URL or resources for a paper or more information on the Keymaker protocol that they could review?
So we have a paper in draft. I'd be happy to share with Moby team to share further as soon as it's published. And also as soon as the GitHub is made public, I can do the same thing, send it over to the Moby team to share it broadly with the rest of the participants.
Great, thanks. Any other questions?
Maybe just following up on the Uber for energy. So that you referenced charging in a sunny area and driving to a cloudy area.
Mm-hmm.
That seems less likely than another type of arbitrage, which is just the intertemporal arbitrage of charging up and waiting for the price to go up and discharging when it does. And unless you're talking about a really severe event, maybe like the Texas grid meltdown, where you can imagine every car within 100 miles of Texas driving to Texas and discharging.
Yeah, no, absolutely. I think arbitrage is more common scenario, in which case this would be useful. The reason I use Menlo Park in San Francisco is because, at Stanford, we talk about this all the time, because there are people who live in San Francisco and work at Stanford, and Stanford has these massive photovoltaic arrays. So, come charge your car on campus while you're working and take it home and discharge it on the grid. So that's why I use that example, not because it's the more common one. Another uncommon example is in disaster relief. So, you could deliver electrons where they needed in events of disaster, assuming the transportation infrastructure is still in place for whatever disaster that is. But you're right, Chris, arbitrage is a lot more common and likely scenario for something like that.
Another question, under what conditions would the physical Uber for energy be better than transmitting via the grid?
I couldn't answer that. It's still a concept. So we haven't really done any work. It's very notional at this stage, but we have power electronics gurus and grid simulation gurus in the team who would be working on that problem when we do get to that bridge to cross.
Okay, great. Any other questions for the chat? If not, we can wrap it up. Let's see. Someone just said, excellent, thank you.
Thank you.
All right, well then, thank you everyone. And thank you, Mayank. This is a great lecture.
Thanks for having me.
Of course. And just to let everyone know, we have this lecture recorded, so it'll be on our website. And be sure to also subscribe to our bulletin and you'll get updates about future lectures. But thank you so much, Mayank, and have a great day, everyone.
Thanks, everyone.